In the previous video, we determined the eigenvalues of angular momentum operators, and now we want to determine the eigenfunctions of angular momentum operators. So the result that we found in the previous video is that if we have the L squared operator acting on one of its eigenfunctions, this is going to be h bar squared L plus 1 times the eigenfunction, and if we have the LZ operator acting on the same f, we're going to get h bar mf. And here L and m are quantum numbers, so obviously these eigenfunctions may very well depend on L and m. And in fact, they will. So this is what we found. And the question is, well, how can we determine the eigenfunctions, and why do we care about this at all? Well, the thing is, remember, these operators are Hermitian operators, which means that they represent observable quantities. So if these eigenfunctions were to be some sort of wave function, then we could apply these operators to the wave functions and determine the angular momentum that these wave functions have. But we don't really know if that's the case, so this is why we actually want to go ahead and find what these eigenfunctions are. So to determine this explicit form of f, we will have to use the explicit form of both the L squared operator and the LZ operator. And with that, we will get a differential equation, well, in fact, two differential equations, because we have two equations here. And when we solve those, we will get the function that we want to find. So let's do that. Let's write now these operators. So let's begin by taking a look at L. Let me just omit for now the operator signs. I put the vector there. Let's just say, okay, L squared. Well, we know what L is. It's just R cross P. So this time, since we want an explicit form, let us write this in spherical coordinates. So R, what is going to be? R is going to be just whatever distance we're dealing with in the r hat direction. And what is the momentum going to be? The momentum is going to be I h bar nabla. And nabla we have to write in spherical coordinates. And this is r hat dr plus theta hat 1 over r d theta plus phi hat 1 over r sine theta d phi. So we have to go ahead and do this cross product. So L is r cross this. So actually, let me just copy what I have here. So this is going to be the nabla, and I'm going to have the r hat cross. Oh, this is minus I h bar, sorry. I like to write it like this, that's why I put the positive sign. I meant to write h bar over I because it's a bit more compact. Obviously, it doesn't matter, these two are exactly the same. Okay, so now we want to do this cross product. We can leave the h bar over I in front. And, well, let's see, the cross product between r and r hat and r hat is going to be 0. They are parallel vectors, so the cross product is 0. Then we have the cross product between, we have r hat cross theta hat. Now, I hope you remember how these cross products go. If not, maybe I'll just do a quick reminder. So if we have these orthogonal systems, now obviously I'm not going to do the complete derivation. You can do that yourself. You probably have done it yourselves, and it's more of a mathematical part from maybe calculus or something where you first encounter these sort of questions. The trick that I like to use to remember this without having to do the calculation each time is to just remember, if you put, for example, x, y, z or r theta phi written like this, and then you have the cross products, then if you're doing any cross product to the right, then you're going to get whatever is to the right of the two that are having the cross product, and with a positive sign. And if you're doing it to the left, you're going to get whatever is to the left with a negative sign. So for example, r cross theta, which are these two, is going to be phi hat with a positive sign. And if you have, for example, phi cross theta, you're going to get minus r hat. And similar with this. Okay, so what are the cross products here? We have r cross theta, which is going to be phi hat. That's going to be phi hat. Then we have an r that cancels out this r over there, so we get the theta. And now we have r cross phi hat. So r cross phi hat. And what is this going to be? Well, this, if we look at this here, is basically going to be r cross phi. So we're going to the left, so we're going to get minus theta hat. So this right here is simply going to be minus theta hat. This r cancels out this one, and we're going to get 1 over sine of theta d phi. Okay, so this is what L looks like right now. And what we want to do next is, similarly as we did the previous time, we would like to find each of the coordinates we want to find Lx, Ly, Lz. So basically the components in x, y, z direction of this vector. But, well, we don't really have it in that form. We have it in form, we have phi hat and theta hat. So we have to write now the Cartesian form of phi hat and theta hat. This is also something that comes from, well, probably calculus, I think, is where you saw this. I don't really remember quite where I first saw this. But theta hat can be written as, I think it's cosine, cosine theta, cosine phi in the I hat direction, plus cosine theta sine phi in the j hat direction, minus sine theta in the k hat direction. And phi hat can be written as minus sine of phi I hat plus cosine of phi j hat. So let's plug both of these into our equation here. So we get h bar over I. And in this first part, it's going to be minus sine phi in the I hat direction plus cosine phi j hat direction d theta minus cosine theta cosine phi I hat plus cosine theta sine phi j hat minus sine theta k hat. And then we have this d by d phi. And what about the 1 over sine? Well, we can actually just let it divide all of this immediately. So this cosine theta will now be cosine divided by sine, which is cotangent. So we get cotangent of theta. This one right here will also be a cotangent of theta. And this sine, it's gonna go away. It's just gonna be 1, so we just get minus k hat. Okay, now since what we're looking for are the components in each direction, let's group all of these terms in every direction. So let's go for I hat. So in the x direction, which is this I hat direction, we have minus sine phi d theta. Then we have minus cotangent of theta, whoops, that doesn't look good, cotangent theta cosine of phi d phi. Yeah, that's everything. Then in the j hat direction, we have cosine phi d theta, and here we have minus cotangent of theta sine phi d phi, and finally we have in the k hat direction we have plus only d by d phi, or in this k hat direction. Okay, so here we have written this in separating into each one of the components, but let's write it down explicitly. So Lx is going to be, let's see, minus h bar over I sine phi d theta plus cotangent of theta cosine of phi d phi. Yes, that's the Lx. Ly is going to be h bar over I cosine phi d theta minus cotangent of theta sine phi d phi. And finally, Lz is going to be h bar over I d phi. And that's it. Okay, so these are now the forms of Lx, Ly, Lz. These are the explicit forms. And the one that we can immediately use is going to be Lz. Because remember, we have the equation for Lz, which tells us that if we apply Lz to some f, that depends on L and M, but I'm going to omit that for now, just for simplicity. This is going to be h bar mf. Okay, so we can now write, instead of this Lz, the explicit form that we just found. So h bar over I d phi of f. This is h bar mf. So here we can cancel out the h bars, and we can solve this equation by separating the variables. So we get df over f equals im d phi. So we can integrate both sides to get that the natural log of f is going to be im phi plus some integration constant that can depend on theta, because this differential equation is with respect to phi. So obviously theta would be some constant when we look at it from the perspective of phi. So this constant can depend on theta. So now we can exponentiate this whole thing, and we get that f is going to be some constant, which I will call now g, times eim phi. So this is the form of the eigenfunctions of angular momentum. We have found the phi dependence, but we have not found the theta dependence yet. And in a very similar form to what we just did, we're going to solve for g of theta by using this first equation. However, we are going to use, we need L squared here. We need the explicit form of L squared. And we don't really know that. This is something I used before. I'm going to get rid of it. So how can we find some explicit form for L squared? Well, let us now remember a little trick that we used before. A few videos back, we saw that we could write L squared in terms of the raising and lowering operators. Okay, so that's what we want to do. And that's also why we found Lx and Ly, because L plus minus is Lx plus or minus Ly. And we know that we can write the L square operator in terms of some product of L plus minus L minus plus. I don't know it by memory, but it was something like this, plus Lz squared, and then it was like plus or minus h bar Lz, something like this. It might not be entirely correct with the signs, but that was the form. So we want to find what this is, and in order for that, we needed Lx and Ly. So we already found that. We now only need to take a look at this. So what exactly is this? Let us use the explicit forms of Lx and Ly that we already saw. So let me go back, see where they are. They are exactly here. Here we are. Okay, so this is Lx, so let me just take it and then plus minus I times this. Okay, now I'm just gonna delete these here since I don't really need it, and this is just L plus or minus. Okay, so I'm gonna move it up. Whoops. Okay, so let's now try to simplify what we have here. So the first thing that we could do, well, Obviously, we can cancel out these i's here. That looks pretty good. What else? Well, we have these d by d theta here, here, and d by d phi here, here. So we could think about factoring out these d by d, these derivatives, and also factor out an h bar. And in fact, maybe it is even better and more comfortable if we just factor out h bar over I. So let's bring these i's back for now, because I think the notation will be better if we leave it like this. So we factor out h bar over I, and once again, just for notation, I will put this minus sign in here. It's the same, I'm just trying to make this a bit cleaner so there's no sort of weird algebraic mistake. And now let's put everything with the d theta together. So this part is positive, so maybe I'll put it first. It doesn't matter though. Minus sine of phi, and then I have plus or minus I times cosine of phi d theta. So here I just use this and this. Next comes all that has this d phi. So I have first minus cotangent of theta cosine of phi, and then I have plus, well, plus or minus, but multiplying a minus sign, so I get minus or plus, because if this was a plus, when you multiply it with minus is a minus, and if this was a minus, when you multiply it with a minus, it's plus. So minus plus I times cotangent of theta sine of phi, and all of this d phi. Okay, making progress. Now, something we can do here is we can factor out the cotangent. So let's do that. So factor out cotangent of theta. And I'll move it all together a little bit. Okay, great. What can we do now? Now let's take a look at what is in here. So this is I cosine phi with this plus or minus sine phi. Here we have minus cosine phi minus plus I sine phi. So both of these things kind of resemble the Euler formula. I don't want to use theta or phi, let's just say alpha. This is cosine alpha, well, plus or minus, depending on whether it's positive or negative, plus or minus I sine of alpha. So these things kind of look like this. So maybe there's a way in which we can rearrange what we have just found to make it look like this, so that we can write this as an exponential, which will seriously make everything much simpler. So let's go for that. Let's see. This part right here is maybe the simplest, and that is, let's factor out a minus sign first. So let's just go step by step. Let's factor out the minus sign. So this minus sign means that this has to be positive, and this right here will go back to just being plus or minus. And as we can see, this is already done. We can just, this is the Euler formula here. So we can just go ahead and write this as E plus or minus I phi. Okay, and what can we do here? So, well, first of all, there's this annoying I here, which is not supposed to be here. It's supposed to be with the sine of phi. So let's factor out an I. So I'm just going to write this here. If we factor out an I, to the minus sign, we need to divide by I, so that when we multiply through, we get back what we had before. And here we have plus or minus just cosine of phi. But this division by I, we can write it. The trick is to multiply and divide by I. And we can actually write it as, well, the I that is outside. And this minus sign will change to a positive, and we'll have an I up here. So we get I sine of theta plus or minus cosine, phi, cosine of phi. So now let's factor out the plus or minus. So we get plus or minus I cosine of phi plus or minus I sine of phi, right? Because this was positive, so if we have a plus sign out here, we need a plus sign here, and if this is a minus sign, we need a minus sign here to make sure that we haven't done anything illegal. So, and this is indeed the Euler formula once again, so this is plus or minus I e to the plus or minus I phi. Okay, so let's plug this into the original equation right here. So this is I e plus or minus I phi. Okay. Now this looks basically as simple as it can get. Obviously we could simplify this part right here, but because of the procedure that we'll do later, I think that it might be convenient to not do it just yet. I might be wrong, but just in case, I'm going to leave it like this for now, and we can always simplify it later. I'm just gonna write it, close it together, and there we go. Okay, so now we know what L plus and L minus are, because L plus is simply this equation but taking the upper sign, and L minus is this equation. Wait, I'm missing the plus or minus sign here, plus or minus. Yes. And L minus is simply this equation but taking the minus sign here. Well, yeah, I almost forgot about the minus sign, plus or minus. That would have been a big mistake. Okay, so now we want to go ahead and rewrite the L squared in terms of these raising and lowering operators. So let's take a look at L plus, L minus. Okay, let's take a look at this product. But for now, still in just this form. Lx minus I Ly. Okay, so if we have this, we're going to get Lx squared. By the way, maybe I should do this in the most general form possible. So just say L plus or minus, L minus plus. So this is plus or minus, this is minus plus. And the reason is because we could write L squared in terms of L plus, L minus, or the product between L minus, L plus. The thing is that doing it with L plus, L minus will give us a much simpler equation to solve. And that is why we choose that form. But just for now, to show you how this is done, even though we kind of did it before, but still I'm going to do it in general. So Lx squared, then we get minus plus I Lx Ly plus or minus I Ly Lx, and then we have plus times minus, minus times plus, so this is always going to be a minus sign, but I squared, which is another minus sign, so we get positive Ly squared. And this we can rewrite as L squared minus Lz squared, because L squared is Lx squared plus Ly squared. So if we had another Lz squared, we would have L, so we can just write it as L squared minus Lz squared. I said L, I meant L squared, sorry. And then we have this part right here. So let me factor out, I'm going a bit faster because we did some of this in the previous video, that's why. Plus or minus I, I'm going to factor from this. So this first part, this is going to be left with a minus sign, minus Lx Ly, and the second part is going to be plus Ly Lx. And in fact, you can see that this is just a commutator between Ly and Lx. And this is the same as minus the commutator between Lx and Ly. Okay, so, and we know what this is. This is simply I h bar Lz. So, considering the minus sign, we're going to get minus I h bar Lz. So, and we're going to have I squared, which is another minus sign, which will cancel out this minus sign right here. So this will simply be h bar Lz. Okay. And this is L plus minus, L minus plus. So we can now use this to write our operator L squared as L plus L minus plus, and then plus Lz squared minus plus h bar lz. Okay. Okay, great. We are making progress here. So what do we do now? Now we need to choose one of these forms. So we can choose either L plus L minus or L minus L plus. As I said, choosing the upper form will give us something easier to work with. If you have never done this before, you could try both and then see which is easier. I'm gonna just save some time and just choose it right away. So we can actually now, this is already the explicit form because we know L plus, we know L minus thanks to this equation right here, and we know LZ. So this already has everything that we need, and we already have everything that we need. So let's now write down our eigenvalue equation that we had, which was L squared acting on F. This is going to be the same as all of this acting on F, which by the way has to be the same as h bar L plus 1 acting on F. So this is the equation that we now want to solve, except that we need to write each one of these terms explicitly. Now L plus L minus, this product is going to be kind of annoying, so let's deal with it separately and then plug it into the equation. So we know that L plus L minus is given by this. And in fact, let me maybe go to a new page so that we can worry about this separately. So what is the product L plus L minus? Well, this is going to be h bar over I. Let me write down L plus. This is going to be positive sign here, so I e to the I phi d phi. And by the way, remember, this is going to be acting on F. Let's not forget that. d theta, sorry, I think I said phi, minus cotangent of theta e to the I phi d phi. Okay, now let's write down L minus. This is going to be h bar, actually, let me leave it outside of the parentheses, h bar over I. And then we have negative I e to the negative I phi d theta minus cotangent of theta e to the minus I phi d phi, and all of this acting on F. Okay, so far so good. Now let's remember what F is. We already know F is going to be some function of theta times EI m phi. So let's write it in that form. This is g of theta EI m phi. So let's see. Here, what can we begin simplifying here? Let's put the h bars together, and also we're going to have I squared, which is minus 1, so we get minus h bar squared here. Now I'm afraid there's not too much more to simplify. We just need to go ahead and multiply through. Make sure to be very careful here. We don't want to be making some unnecessary mistakes. So this first part, multiplying this right here, or acting on it. Now we get I EI phi d theta of this right here. So minus I e minus I phi d theta, and this is acting on g of theta EI m phi. Okay, so this is the first term. We will simplify it in a bit. Now the second one, that's going to be minus, by the way, the second one is going to be this acting on the second one right here. So we're going to have I e I phi, so plus I e I phi d theta, and this thing right here, so minus cotangent of theta e to the minus I phi d phi, acting on g of theta e I m phi. The third part will be this right here acting on this. So that's going to be minus the cotangent of theta EI phi d phi of minus I e to the minus I phi d theta, and this acting on g of theta ei m phi. Okay, the final term is now going to be minus cotangent of theta ei phi d phi, and this is acting on minus cotangent of theta e minus I phi d phi acting on g of theta ei m phi. This and this, and I think I'm missing one more. Okay, so we now have 4 terms that we need to simplify. So let's pick them one at a time, take them to the next page, and work them and just simplify them. Okay, so new page. Okay, so this is going to be what? Well, we have I, and in fact maybe let me just simplify it right here. This is going to give us a minus sign, which will cancel out this minus sign. And then we have this exponential right here, which will not be affected by the partial derivative with respect to theta. So this one will cancel out this one right here. And then all we are left with is actually the second derivative of g, whatever this function is, times ei m phi, since this is not going to be affected by the partial derivatives in theta. So let me go back here, delete this thing here that we just took, and write it, whoops, as this. Yes, because this cancels out the minus sign. Okay, great. Second term is this one right here. So let's take it now here to examine it. Okay, so what can we do with this? Let's see. Well, first we are going to have to apply the derivative. So we are going to have the same thing, ei phi d theta. Well, we can leave the minus sign outside, cotangent of theta e to the minus I phi, which we can actually take outside as well and have it cancel out this right here, since it isn't affected by this partial derivative. And this derivative right here is going to be I m g of theta ei m phi, since this g function is unaffected, and the derivative of the exponential is going to be I m times the exponential. So by doing that, we're going to get I squared, which is going to give us a minus sign, which will cancel out this minus sign. Okay. Now, well, we can just take the minus sign outside, actually, the m, sorry, this m, and also the exponential. So let me maybe just rewrite it, m ei m phi d theta of the cotangent. I think that the best, if you don't know the derivative of the cotangent by memory, the best way would be to just write it, at least for me, as cosine theta times sine of theta to the minus 1 times g of theta. That would be the easiest way for me to write it. And let me now just delete this part right here, so that we can worry only on calculating this derivative. So what is this derivative going to be? Well, let's apply the product rule 3 times. So we get m ei m phi. So for the first term, we get minus sine of theta times sine of theta to the minus first power g of theta. So the signs will cancel out, and we are left with only g of theta. Okay, let's now apply the derivative to the sine of theta to the minus first power. So this minus 1 comes down, so we get minus this cosine of theta, and then we have sine of theta to the minus 2, and times the derivative of this, what is inside. This is the chain rule. So that's going to be another cosine theta, so we can just write it as cosine squared, and times g of theta. And the final term is just deriving g, so we can just write this cosine sign as cotangent once again. So we get plus cotangent of theta g prime of theta. And this cosine squared times sine to the minus second power, this is just the cotangent squared. Okay, so now we have this second term. Let's go back and plug it into our equation. So this right here has been simplified, and it is this. Let's now go for the third part. Okay, what can we do here? Well, first let's apply this inner derivative. And let's take this minus sign outside, so it's actually going to be positive. So we're going to have I cotangent of theta ei phi d phi of e to the minus I phi, and this derivative will simply be g prime of theta ei m phi. So here let's rewrite the exponentials as e to the I m minus 1 phi. Right, so just put them into a single exponential so that it's easier to apply the derivative here. So when we do that, we get I cotangent of theta ei phi times, well, g prime of theta, this is unchanged, times I m minus 1 e to the I m minus 1 phi. So here we can simplify a few things. So this I right here and this I right here will give us a minus sign. Then this exponential will cancel out this minus 1 right here. So this is just going to be ei m phi. And yeah, I think that's it. That's all we can simplify for now. So let's plug it back in here. So there's just one final term that we need to simplify, and it is this one. Okay, so all of these derivatives are with respect to phi, so let's take the cotangent outside and the minus sign cancel out, so we get cotangent squared of theta ei phi partial derivative with respect to phi of, well, I minus I phi, and when we apply this first derivative we get, well, this g function is going to be unaffected. Let's actually just write it outside, and we're going to get I m ei m phi, but we can actually just combine our exponentials as we did last time as ei m minus 1 phi, so that when we now apply the second derivative, we're going to get everything that we had outside, ei phi times I m times I m minus 1 e to the I m minus 1 phi. And here once again, this exponential will cancel out the minus 1 part, so we're going to be left with I m phi. These i's will give us a minus sign, and let's just group everything here together. Okay, and I'll just put this back here. Okay, hopefully there's no algebraic mistakes anywhere, but this is now the product L plus L minus. So now let's plug this into the actual equation, because remember, the actual equation is not just this L plus L minus part, but it is what we had here. It's L plus L minus plus, by the way, this, maybe I should write it further down here. It kind of looks like it's a minus sign, it's just L minus. So let's put it here. So this is the first part of the equation, just L plus L minus. What is LZ squared acting on F? We know that. That is h bar over I. Let me use the same color actually. That is h bar over I squared d squared F d phi squared, because we know that LZ is h bar over I df d phi. We found that when we solved the first equation at the beginning of this video. And then we have minus h bar from here, LZ, which is h bar I df d phi. So let's now find these well, actually we have already seen them, right? But just to make sure, df d phi, this is simply g of theta ei m phi times the derivative of this exponential, which is im, and the second derivative, d squared f d phi squared, this is going to be minus m squared g of theta ei m phi. So let's write these things into this. So this is going to be minus this m squared g of theta ei m phi, and then the first derivative is simply g of theta ei m phi times im. And all of this, remember, has to be equal to h bar squared l plus 1 times f, but f is g of theta ei m phi. Okay, we are making some progress. Now let's simplify some of the things that we can here. So first of all, we have this I squared down here, which is going to give us a minus sign, which will turn this minus into a plus. We also have this I right here, which will cancel out with this one. And also notice that there is an h bar multiplying everything. So this h bar, well, I didn't want to get rid of the minus sign. This h bar is going to cancel out with this one. Basically, we are just going to divide everything by h bar squared. There we go. And also every single term has EIM phi, so we can actually divide by that as well, since it's also never going to be 0, so there's no problem in doing that. Okay. So now it's looking a bit better. We still have these parentheses that are kind of annoying, so let me multiply through by these quantities. So this first part will be minus m times the g function, and then we have, and actually let me get rid of this plus sign. Then we have minus this thing times m. M is just a number, so you can write it whatever you like. And this final part here times m. And we also have this minus sign out here. So let's flip all of the signs. So this is negative, this is positive, this is now positive, this is now negative, this is now positive, and this is now positive. So we can get rid of this and of this. Okay, now, is anything else canceling out? Let's see, we have here negative mg, and here we have positive mg. So this and this cancel out. What else? Let's see. Here we have two terms. One of them is going to be m squared g of theta cotangent squared of theta, and the other one is going to be minus m g of theta cotangent squared of theta. And this is actually the same as this right here. So that part will cancel out, and we will be left with, I'm going to write it back here in white, m squared g of theta cotangent squared of theta. And I think that's everything that cancels out, right? Cotangent g prime minus cotangent g prime. Well, I'm going to now group everything together, and if there's anything else that cancels out, it's going to, we're going to see that very soon. So let's now write it down here. I'm going to change color to make sure that we see that this is different. Let's group all the orders of derivatives together. So here's the second derivative. Now let's just put g prime of theta factor of, let's see. Well, we already included this part. We have here minus m cotangent of theta. And here we have, let's actually write it separately because there are two parts here. So let's write it as plus m cotangent of theta, and then we have minus cotangent of theta. So these parts here will cancel out as well. So let me actually just erase them. And I think that's everything that involves the derivative. So let's now put everything with the g together. So, oops, wrong color. So plus g of theta factor of, we are going to have here m squared cotangent squared of theta, and here we have m squared, well, times g of theta, but that's already factored out. And this is equal to L plus 1 g of theta. Okay, so let's now continue simplifying this. So we get minus g prime prime of theta. These are obviously a derivative with respect to theta. Minus cotangent of theta g prime theta. And then we have, let's take a look at this. So we can factor out m squared here. So m squared g of theta. And then we have cotangent squared theta plus 1. And what is that? So cotangent squared, this is simply cosine squared of theta divided by sine squared of theta. So if we now go for a common denominator, we can write it as cosine squared plus sine squared of theta, and all of that divided by sine squared. But cosine squared plus sine squared is 1. So this is simply 1 over sine squared, which is the same as the cosecant of theta squared. Okay, so we got this part, and now we can actually just go ahead and put minus L plus 1 g of theta equals 0. Okay, we are now almost done, and you might actually begin to see where this is taking us, but I won't spoil it in case you haven't seen it. So let's actually now write it in a slightly different form. I'm just going to factor out these terms here. So g of theta times m squared cosecant squared of theta minus L plus 1 equal to 0. So now let's multiply, because the cotangent here, just to make it apparent, this is cosine theta divided by sine theta. This here is 1 over sine theta squared. Oops, I didn't erase that. So let's multiply through by minus sine squared of theta. Okay, so when we do that, we're going to get sine squared of theta g prime prime theta plus sine of theta g prime of theta minus, well, actually let's put the minus in here. So g of theta, then we get L plus 1 sine squared of theta minus m squared, and this is equal to 0. And I hope that this is ringing a bell. If it isn't, let's now use a simple it's a trick. I don't know if I want to say simple though, because it can be somewhat hard to spot, but let's take a look at this. So what if we have sine of theta of the derivative with respect to theta of sine theta, the theta of g, right? If we had this, let's just do the operation. So this would be sine of theta, and then what do we get? We get d theta. Oh, by the way, I missed the cosine. That's why this was looking weird. I missed it. I don't know why I canceled the cosine here. It's sine cosine, sorry. Yes, that's why it was looking weird. Okay, so we have this sine theta, and then the derivative of this, which would be, well, derivative of sine is going to be the cosine of theta times this. This is the product rule, d theta, which we might as well just write as g prime. It's what I wrote as g prime before, plus sine theta. And well, then we have the second derivative. Let's just go back to this notation so that it is consistent. So just g prime of theta, and here too, g prime of theta. Okay, so if as you can see, this is the same as what we had before. This term is this term is this. So we can actually rewrite what we had here as, whoops, didn't mean to change colors, sine of theta, d by d theta of sine theta dg d theta. And here I did change the notation on purpose because I want you to see this equation and hopefully recognize it if you have been following my lectures on quantum mechanics, because we already encountered this equation before when we were solving the angular equation for the hydrogen atom. This right here is what we solved, and the solution combined with, of course, the EIM phi is what we called these were the spherical harmonics, right, which is dependent on L and M. This was some polynomial, right, which we saw are the associated Legendre polynomials, times PLM of cosine theta times the EIM phi, right? And this is what we saw were the solutions. So there's no need to solve this again. We already know the solutions are the spherical harmonics because this is the exact same equation. And this is actually quite interesting because these are this is our f function, right? Because this right here gave us this part of the solution, and when we put it together with what we already found, because f was g of theta EIM phi, so g of theta are now the spherical, well, not the spherical harmonics, these are the associated Legendre polynomials. So yes, this is now the solution. And why is this important? Because let me now go back to what we saw at the beginning, what we were talking about, the motivation behind all of this. We know now that the eigenfunctions or eigenstates of these operators are the spherical harmonics, which are also the eigenfunctions of which important operator? Of the Hamiltonian operator. Whoops. Right? So that means that since they have the same eigenfunctions, then the Hamiltonian operator commutes with these L squared and LZ operators. And this is very important because now we know that we can let these operators act on these functions of these physical states for which the solutions are the spherical harmonics, and we can determine their angular momentum with these very simple formulas. And we can also, to those states, apply L plus and L minus. That's very important, and continue to find the angular momentum states. So that's actually extremely important because now we can apply the angular momentum theory to all of this. And there's actually another important remark, because we saw in the previous video that L can be half integer. L, we saw, can be 0, 1/2, 1, 3/2, 2, and so on. But in what we discussed back in the hydrogen atom, L was an integer, and this is not the case this time. This time it can be a half integer. So it is weird that now there are cases that allow, for some reason, this half value for L. And for now, we don't really know what it is, but that's actually going to be the topic of the next few videos, because that's where we will find what is called the spin, the angular spin, which is, or angular spin moment, well, it's fine, the spin, which is a form of angular momentum, which we have now seen appears, even though we haven't really gotten to go into that subject just yet. So if you have any questions, let me know down in the comment section, and I will see you in the next video.